So let's start the chapter by reviewing relations. Ordered pairs are two numbers written in a specific order, the x-coordinate first, the y-coordinate second, and can be used to show the values of a point on a graph. A relation, in this case denoted with the letter R, is a set of ordered pairs. So we have three ordered pairs here, and we see that the first number in each pair represents the x value, or the x-coordinate of the point, and the second number in each pair represents the y-coordinate, or the y value, for each point. And the reason this is important is because a function is a relation in which each x value has one y value associated with it. So in this case, we have the relation h, and we see we have 4 points in this relation. Now the x values are considered our input values. They're the number we plug into the function. And the y value is considered the output. And we'll discuss this further a little bit later in the chapter. But we see here for our 4 points, we have x values of -3, -2, -2, and 0. And for our y values, we have 5, 2, 0, and -2. So we have -2 twice for our input values, and each -2 is associated with a different output value, 2 and 0. So since this input, -2, can provide two different outputs, that lets you know that h is not a function. Now, let's review a few different types of functions. A linear equation is a function because there is only one y value for each x value. So here's an example of a line. And a line in general has the basic equation of y is equal to x. They both have an exponent of 1. And again, a line will look different on a graph based on the slope or constant added. But the general formula is y is equal to x. And you get a straight line through the graph. And for each x value, there's only one y value associated with it. A parabola that opens up or down is a function because there's only one y value for each x value. The general formula for a parabola that opens up is y is equal to positive x squared. And we see for each x value, there's only one y value associated with that x. If we go up and down, there's not another y value associated with that point. If we flip this parabola upside down and now it opens down, we can use a vertical line again to find if there's a second y value associated with each x. So at this point, there's only one point above or below. At this point along the curve, there's only one point here. At this point of the curve, this is the only point. If we go up or down, we don't find another y value associated with this x. But in the case where the parabola opens to the left or right, it is not a function because there are two y values for certain x values. So the general formula for parabolas that open to the side is x is equal to -y squared. And now when we draw a vertical line, we see that for this x value, we have 1 and 2 y values. So since this vertical line can cut through two different parts of the curve, that lets you know this is not a function. Same thing at this x value. We have a y point here and a y point above here. If we flip this parabola to the right, the general formula is x is equal to y squared. And again, a vertical line shows us that for certain x values, we have multiple y values associated with that x. Have a y value down here, and we have a y value up here. Another example is a circle. A circle is not a function because there are two y values for certain x values. The general formula for a circle is x squared plus y squared is equal to r squared. And if we use a vertical line, we see that for certain x values, you have multiple y values associated with it. Go to this x point, we have a y value here and here. So we see a circle is not a function either. So we notice that a vertical line can be used to help us figure out if a curve represents a function or not. If a vertical line can intersect more than one point on the curve, then the graph is not a function. Very important. We'll be utilizing this throughout the entirety of this chapter. Let's now take a look at explicit versus implicit form. Explicit form of a function is written in terms of an independent variable, in this case our x, with the variables on opposite sides of the equal sign. So we have y, which is equal to f of x. So y is the result of plugging x into the function f, and x is our independent variable. But we can also have y is equal to f of x, which is equal to x plus 2. So we plug in a value for x, and the output will be y. This is explicit form. Our y and our x are on opposite sides of the equal sign. This would be another example. F of x is equal to 3x minus 5, and f of x represents the y value at a specific x value. So this is explicit form. Implicit form of a function is written with the two variables on the same side of the equal sign. So 2y plus 3x is equal to 5. We still have the same variables, but now the x, instead of being on the right side, is on the left side, along with our second variable. So that is the difference between explicit and implicit form. Let's now begin discussing how we go about evaluating functions, and we'll begin by discussing function notation. Function notation is the way a function is written. A function can be represented by any letter, but the most popular function notation is f of x. So when we are dealing with functions, we choose a letter to represent that function, and beside that letter, we have a pair of parentheses with a letter inside of it. The letter inside of the parentheses represents the independent variable for the expression. So the value of the function will be based on the number or expression that you plug in for this independent variable. Now we state this function as f of x, but both the letter representing the function and the letter representing the independent variable can be changed. So we can also have m of x, and now this function is represented by the letter m. We could change the letter representing the function or the independent variable itself. So this would be called h of k. But this doesn't change how you go about evaluating the expression, since you know the letter inside of the parentheses represents the independent variable, and the letter to the left of this represents the letter for the function. Okay, so just keep this in mind. Now, notation shows the y value associated with a specific x value of a function. So let's say we had a coordinate plane with this function in it. F of x is equal to x plus 1, which is equal to y. So if this is our function, the input is the letter inside of the parentheses, which is x. That's our independent variable. So when you plug in a number for x, you'll get an output that correlates to this expression here, x plus 1. And the result of that expression will give you the y value associated with that specific x value. So let's say we plugged in -1 for x for this expression. That means the function has a value of 0 along the x-axis where x is equal to -1. So you go to -1 along the x-axis, and the function has a y value of 0. And this can be expected since the function had the expression x plus 1. So -1 plus 1 will give us 0. Let's say we plugged in a different number for our x. If we plugged in 0, that would give us 0 plus 1, which gives us an output value of +1. So at 0 along the x-axis here, the origin, we see the function has a y value of +1. Let's say the input was +1 instead. The output would be equal to 1 plus 1, which is a y value of 2. So we go along the x to +1, and we see the function has a y value equal to 2 here. So this is the general process of evaluating a function. Now, evaluating a function means substituting a number or expression into the function for the independent variable. So let's say we had the function f of x is equal to 5x plus 6, and you were asked what is f of 3 equal to. What this question is asking you is if you go to 3 along the x-axis, what is the y value associated with this specific x for the function? So let's dive a little bit deeper into how we go about evaluating functions. Let's say you were given f of x is equal to 5x plus 6, and you were asked what is f of 3 equal to. You could also be asked what is f of x plus 1. The input does not have to be a numerical value. It can also be an expression. And the function itself will wind up changing since we don't simply have x inside of the parentheses. But we'll take a look at this in a second. Let's start by substituting a number into the expression. So if we're evaluating a function substituting a number, the first step is to substitute the number inside of the parentheses for x. So we were given f of x is equal to 5x plus 6. So we want to substitute the number inside of the parentheses, which would be 3, in for x. When we do so, that gives us 5 times 3 plus 6. And now, step 2, we want to simplify the expression. So 5 times 3 is 15. And 15 plus 6 is equal to 21. So we see f of 3 is equal to 21. So when you're given a function and a number is substituted in for the independent variable, you substitute that number in for x, and then you simplify the expression. But what do we do if we're substituting an expression instead of a number? Step 1, substitute the expression inside of the parentheses for x. So again, our function is the same. F of x is equal to 5x plus 6. But now inside of the parentheses here, we have x plus 1 instead of x. So we substitute x plus 1 everywhere we see x in the expression. So we get f of x plus 1 is equal to 5 times x plus 1 plus 6. Instead of x here, we have x plus 1. And now, step 2, simplify the expression. So we want to evaluate this term here first. So we have 5 times x, which gives us 5x. And 5 times 1 will give us 5, plus 6. And now we want to add 5 and 6 to give us 11. So we see f of x plus 1 is equal to 5x plus 11. So when we substituted a number in for the independent variable, the final result, the output, was a numerical value. But when we substitute an expression into the independent variable, we wind up with an expression as the final result. So the outputs will be different whether you're substituting a number or expression. So just keep that in mind. But now that you've had a chance to see an example of both, let's now have you try a few practice questions. Given that f of x is equal to negative 2x plus 4, question number 1, what is f of negative 3? Question number 2, what is f of 5? Question number 3, what is f of x minus 2? And question number 4, what is f of 2x plus 1? Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, substitute the number inside of the parentheses for x. So the independent variable is x, and the question asks us what is f of negative 3. So we plug in negative 3, each place we see x, which is here. And now step 2, we want to simplify the expression. So we start with negative 2 times negative 3, which will give us positive 6, plus 4. So we see f of negative 3 is equal to 6 plus 4, which is equal to positive 10. So the answer to question number 1 is f of negative 3 is equal to 10. Question number 2, we have the same function. The question asks us what is f of 5. So step 1, substitute the number inside of the parentheses 5 for x. And now we want to simplify the expression. So we start with negative 2 times 5, which gives us negative 10 plus 4. Negative 10 plus 4 is equal to negative 6. So the answer to question number 2 is f of 5 is equal to negative 6. So that is the answer to question number 2. Let's now have a look at question number 3. Step 1, substitute the expression inside of the parentheses for x. So instead of a numerical value, we have the expression x minus 2. So we want to substitute x minus 2 where we see x, which is here. And now we want to simplify the expression. So we want to distribute this negative 2 to both terms inside of the parentheses, which will give us negative 2 times x, which is negative 2x. Negative 2 times negative 2 is positive 4, plus 4. And now we combine positive 4 and positive 4 to give us positive 8. So we get f of x minus 2 is equal to negative 2x plus 8. In question number 4, we have 2x plus 1 as the input value. So we want to plug that in each place we see x, which is here. And now we want to simplify the expression. So we begin by distributing this negative 2 to both terms inside of the parentheses here, giving us negative 2 times 2x, which is negative 4x. And negative 2 times positive 1 is negative 2, plus 4. Negative 2 plus 4 is positive 2. So f of 2x plus 1 is equal to negative 4x plus 2.